This is a nice question about proof. Part C is actually something that's on the A-level syllabus that you should have learned anyway. So actually it's quite nice as long as you've practiced that proof to get those 5 marks. A and B though, I like them because they're talking about alternative methods to trying to show that there's an infinite number of prime numbers and why the proof fails because of the assumption. And we just have to show that the claims are incorrect. So the student claims in their proof that if p is prime, then n equals 2p plus 1 is also prime. And we're asked to show using p equals 7 that this is not true. So if p equals 7, then 2p plus 1 is going to equal 15, which is 3 times 5. Therefore, 2p plus 1 is not always prime. That is our counterexample. That is enough. In B, the student changes the proof to n equals 6p plus 1. Instead of 2p plus 1, we have to show that this also still fails. So if you go with n equals 7, actually, now you get p equals 7, you get n equals 43, so it actually doesn't fail. And if you work your way up through them, like 2 gives 13, that's prime. 3 gives 19, that's prime. 5 gives 31. You can quickly see that actually it doesn't seem to be failing for small primes. Well, to be honest, when I did it, I just kept trying. So 11 gave 67, no. 13 is 78 plus 1, 79, no. 17 is 60 plus 42, 102 plus 103. What about 19? 6 times 19, that's the same as 6 times 20, minus 6, so 114. And then if we add 1, we're actually going to get to 115. And in fact, you could use any prime number that ends in a 9 because that will necessarily make this end in a 4 and hence the overall number end in a 5. You have to go quite far though for it to fail. So for B, let P equal 19. Then N is going to equal 115, which is actually 5 times 23. So N is not prime. There we go, counterexample to this one as well. Finally, we're asked to write out a correct proof by contradiction to show that there's an infinitely many prime numbers. So our starting point is to assume the opposite. Assume there are a finite number. And list them. So we've got 2, 3, 5, 7 onwards until we get to the very last one. I should say largest prime. Okay, and then we're going to let capital N be a product of all of these. Sorry, that's meant to be a times. So every single prime will divide into n, but then we're going to add 1 to it. N minus 1 is divisible by every prime, but n will leave a remainder of 1 when divided by any prime. Therefore, it is not divisible. Therefore, it is not divisible by any prime. So and numbers are either primes or products of primes. We're kind of assuming that here, but it is true. I should probably just add that these are whole numbers. So n must be prime, since it's not a product of primes. Also, it's clear that n is greater than the largest prime. And therefore, n is a larger prime than Pn. But this is a contradiction because we said that Pn was the largest prime. And the only conclusion that is possible is that our original statement that there's a finite amount of primes must be incorrect. Therefore, there are infinitely many primes. So of course, don't try to learn this word by word how I've written it. Add your own little flair to it, however you want it. But the main idea is that we list all the primes. Make sure you start at some point introducing p's in the solutions. They even go straight for p1, p2. I quite like to actually write down the first few. Number 1 is not prime. And then we construct this n as the product of all of them plus 1. See that that is not divisible by any prime, so n must be prime. N is also larger than Pn, so we've got a larger prime, but this is a contradiction, and the only conclusion is that there's an infinite number. Well done.